So here I've got more space drawn out so we can do this reaction. So we recognize that this is going to be HCl plus NaOH. We know the products are salty water, H2O, and NaCl. All right. I'm adding, let's see, 25 milliliters of this plus 25 milliliters of this. And there's a couple things that I need to know before I can proceed. And it's just like that first problem I did. Okay? So I'm going to assume the density of this whole mixture is 1 gram per milliliter. You know, maybe if I was told the density, then I could use it. But given that this is aqueous, right, and water is a product, I'm just going to assume the density is 1 gram per mil. Okay? I can do that because I'm a professor. So we're going to assume 1 gram per mil. I'm also going to assume the heat capacity of the mixture is 4.184 joule per gram per degree C, which is the specific heat of water. So if I'm assuming the density of the solution is that of water, I also have to assume the heat capacity of this reaction is that of water. And that's a good assumption. Both of these are good assumptions because these solutions are aqueous. Okay? So we had to know that before we can even proceed to any kind of calculation. All right? And so what we also need to recognize, well, what equation am I going to use? Well, I'm going to use Q equals M times CS times delta T. Okay? And now, because I'm doing 25 mils plus 25 mils, and I'm assuming it's 1 gram per milliliter, this means my reaction mixture is going to be 50 grams. So 50 grams for this reaction mixture. Okay? And so very quickly I can plug and chug away. I can say for M, 50 grams, we're going to use 50 point. Okay? Because I have 2 sig figs at the 25. So 50 grams. And then CS is 4.184 joule per gram per degree C. And then now what about my change in temperature? Well, my T final, look, check it out. T final minus T initial. The final temperature was 25.0. The initial temperature was 18.5. Quick math, that's 6.5 degrees Celsius for my change in temperature. Okay? So now when I go and calculate this, okay, so 50 times 4.184 equals, and then times 6.5. So let's see, that comes out to be 1, 2, 3. So 1 point, we use 2 sig figs, 1.4 times 10 to the 3 joules, which is the same as 1.4 kilojoules. So now that's how much heat was released. But look, it's asking me for the delta H of the reaction. This number is not it. This is the Q. That's the heat released, but it's not the enthalpy of reaction. Okay? So I need to figure out how many moles reacted. Because remember, these delta H's have to be kilojoules or joules per mole. So here's what I know with my HCl. Okay? And I could do the same with NaOH because they're both the same volume and molarity, right? So I know that there was 25 milliliters, okay? And so I'm trying to convert this into moles. So what I need to do is first get that into liters, okay? Because I was told that it's 1.0 molar HCl, and so that means it's in 1 liter, there's 1 mole, okay? So when I go through and do all this, 25 divided by 1,000 times 1, I get 0.025 mole of HCl reacted or of NaOH reacted, because they're the same in this problem. And so now that means my delta H is 14 kilojoules divided by 0.25 moles. So let's say divide by 0.025, and that gets me 54.4. So with 2 sig figs, that's going to be 54 kilojoules per mole for the delta H of reaction. So there's a couple things going on in these calorimetry experiments. Just to summarize, for one, we can see if a reaction is exothermic or endothermic based on if there's a temperature rise. If there is a temperature rise in a calorimetry experiment, it's exothermic. If there's a temperature decrease in a calorimetry experiment, it's endothermic. We can calculate how much heat evolved in the reaction, so the total amount of heat. So this Q value, that gives me my total heat evolved. And then when I divide my total heat evolved by the number of moles that reacted, that gives me my delta H of reaction. Okay. So what does a professional calorimeter look like? So this is a bomb calorimeter. I actually have one of these in my laboratory that senior students get to use. It's pretty cool. And so what you do in these bomb calorimeters, it actually is a bomb. It's a stainless steel bomb. And you put your reactants in there and you wire up these ignition wires. And you fill this whole thing with tons of oxygen gas. So there is a lot of chemical potential in this thing. Okay. And note, in bomb calorimetry, you typically study fuel or food. So specifically, bomb calorimeters are designed to do calorimetry on fuel or food. With respect to food, you get what's called the fuel value. So that actually tells you like how much energy you get out of this fuel. With food, you can actually get the caloric value using this bomb calorimeter. Okay? So in other words, what you're doing in this experiment, CXHY, so some organic molecule, some hydrocarbon, you add a large excess of oxygen to this bomb calorimeter, so there's no limiting reagent issues in this device. There is a ton of excess oxygen flooded into this thing. And of course, it completely combusts into CO2 and H2O, which is the same equation overall that your body goes through to do for respiration, right? Proteins and sugars plus oxygen to make CO2 and water, or for fuel, okay? And so what ends up happening is this whole thing is surrounded by water to keep it safe, because there's an enormous amount of energy released in these bomb calorimetry experiments. So all of that energy is absorbed by the water. So in this measurement, in this instrument rather, the change in temperature is indicated by the water. So there might only be a couple degrees change in temperature due to the water, because water has such an enormous heat capacity. If this water were not there, it would blow up. It's a bomb, right? So you have to make this thing useful. You know, it has to be able to be used in a laboratory and not like explode the laboratory. So this is very cool. We do experiments with this in my lab with the seniors, with the physical chemistry students, and they dig it. It's kind of fun. We can put all kinds of junk in the bomb calorimeter and blow it up. Super cool. Okay, so that is, I'm going to cut it off there for this lecture. And I think I'll just have one more video after this. Okay, folks, I'll see you later.